Attaché bij pak. Ik de screen.
Po, duket.
Duket, po duket shumë mirë.
D'accord. My midterm project involves the use of SVD, singular value decomposition, for image classification. Before we get there, we are going to explain singular value decomposition in a bit of a geometric view. So this is for our purpose especially. Now, matrix multiplication is one of the key ways through which vector position and modules are manipulated. We multiply a vector with a matrix or a vector with another vector, and the vector itself comes out different. This happens in two specific ways. For those of you who took linear algebra, you may remember this as the spanning of a space. So either by changing the angle or expanding and contracting the length of the vector. When represented graphically, this leaves us with the aforementioned basic processes. The rotation of a vector by a certain angle and the extension or compression. The book uses the term stretch in this case, but I've called it extension. It's the same thing. You just change the length, multiply it by 2. As you can see here in picture C, it grows. The image that we have for SVD, or an image of how it works, is that of a unit sphere, a sphere with a specific radius, which is then either stretched or rotated in accordance with an MXN matrix. So the matrix is like a function or like an operator, which takes the sphere as an input and produces this hyperellipse as an output. The hyperellipse is nothing to be confused at. For example, a hypersquare is just the square taken to different dimensions. A point, a line, a square at 2 dimensions, a cube at 3 dimensions, a tesseract, which is some of you may have seen in the cube, inside the cube that rotates, etc. A hyperellipse is an ellipse of n dimensions because, of course, we can. The reason we do this is so we can be able to operate with very high dimensions. What we see in the unit sphere S with axes V1 and V2 is being transformed into the hyperellipse AS. So the sphere S is multiplied by the matrix A. The axes of the ellipses are the sigma 1 U1, sigma 2 U2. U refers to the orthogonal directions, so the basic directions in whatever level of space we are. In 2-dimensional space is vertical, horizontal, x and y. In 3-dimensional space, x, y, z, etc. Of course, we don't visualize m-dimension space when we're going there, but we assume it mathematically. So we can't consider, for example, 6-dimensional space. It's just how we assume it is. In other words, the sigma times u product refers to how much the ellipse stretches in accordance with a certain dimensions. For example, vertically, it stretches this quantity. Horizontally, this much. And it produces various different shapes. It can produce every sort of different shape in this product. So, what do we have here? We have the radii of the sphere, V, when modified, not multiplied in this case, but technically we're modifying them by A, produce this sigma times U product. So the axes we had are modified through some process and produce different axes in different directions and different lengths. We can already see how this could give us a singular value decomposition. How we could go, how we could take this matrix A and derive from it 3 main components, simply by taking the V onto the other side. We have to invert the V, obviously, which is why it has this, sorry, my bad, this little sign here. These 3 components, V, the originals, U, and sigma, are how we will also be expressing SVD in the future. As we can see, this is the now here is something to discuss. This gray box and this gray box over here are artifices. Basically, in our concept, U is without this part and sigma is without this part. But we add them so that matrix multiplication can proceed smoothly. For example, this matrix, as it is, cannot be multiplied by this matrix, so we have to add, for example, These are just rows of zeros. This is the diagonal matrix, but it needs these rows of zeros so that it can actually be multiplied, it can have the correct dimensions. This is a very simplified look into SVD, of course. Now, where do we go from here? We go into machine learning. How can we combine these two? One of the modern uses of mathematical concepts, of course, is their application to machine learning. We allow a machine to learn in a way that reminisces the way the human brain works by feeding it various mathematical algorithms. Some are better for certain tasks, some are worse for certain tasks. This is not really the purpose of this presentation. By developing these mathematical algorithms, they match the way you perceive and calculate things. And they can even become capable of recognizing images the way we do. We'll have a case of how human perception and machine perception differs. Right here. This is a specific breed of dog, the Dachshund, I believe, where this is a very minimalistic drawing of, just supposed to be a drawing of this dog. Even then, even though there's in pixels and in pixel values, there's a tremendous difference between this image and this image, the human eye and the human brain can perceive this one as a drawing of this dog species. We know, for example, when we see this is a dog, this is a drawing of a dog. Okay, we can say it's bad or good, but still, we are able to recognize what this image represents and categorize it. And this is what we're trying to do. Now, what does this sort of imagery tell us? Just one second. It tells us that one of the key features, this is actually a drawing by Picasso, by the way, not very relevant, but still, it tells us that this picture is has very pronounced edges. So perhaps edge detection could be what's key to this, and we will see that indeed it is these well-pronounced edges that help us create these categories. This is a data set of cat and dog images in black and white. The data set that would be used in this project as well. Of course, these are not all of them, it's just examples. These are the dogs, and these are the cats, 9 by 9. This is the code. We first load both data, and we create wavelet transforms. They're a bit complicated, so we're not going to explain them right here. But first, we need to put them through this process before we can take them to the CVD. Now, DC trainer is a function which we will see after a bit, but it, as we can see here, USV, which is related to letter sigma, it produces the results of singular value decomposition. And here is the function. We take it's a DC wavelet. We create, we determine the wavelet resolution. It doesn't have to be 32 by 32, but in this case, it is the chosen one. We need, the files actually are at the 4096 pixels, but we need to reshape them into a proper square image. This is what this one does. We proceed by encoding data. We reshape the DC data, and this is the function. This simply prepares the image, as to say, and converts it to the grayscale that we need it for, so that classification goes smoothly. We proceed with the other side, the dogs as well. This is the basic SVD function, specifically reduced SVD. Reduced SVD, if I'm just going to go back a few slides real fast and come back here. Reduced SVD is SVD without this and this. Here we are. We proceed to derive just the SV product. And as you can see here, we have the U, the dogs, and the cats group. Now, this is what the program actually does. What can we see here? This is a highly blurred. The effect is not actually blurred. It's not actually blurring, but it looks like blur. Cat image, and this is the final product. Now, if you may notice, along this line and along this line, as well as here and here, certain regions of interest are forming. These are the edges. For example, we will determine, or the machine will determine, that the way that the cat images are classified so easily is because of the prominent and upfront triangular ears. These ones. This is then the data which we derive. We can see some similarities between the dog side and the cat side. For example, this doesn't fluctuate as much as this one. This one is a bit more stable too, whereas this one has more extreme values that go on the lower side a lot. This one is almost entirely positive, whereas this one is very much negative. Here we have a lot of fluctuation compared to the two before, but we see the cats are even further than that. So we can clearly categorize these images along two different groups. These are these statistics more accurately. So this is what my project is about. Using SVD and separating the image to the components, which actually is its own discipline on the side, ICA, image component analysis, but it's not part of what I was doing. And then using these components, we further are able to determine what the image is along a certain classification. It's not limited to cats and dogs, obviously. This is just one of the most famous applications. Any questions?
Okay. Ari, you turned off the sharing screen, I guess?
Yes.
Okay. Can we have a look back at the last 3 slides? I just want to have a look. So,
Of course.
or anyone else has any question for Ari's presentation? So he has used singular value decomposition of the respective images of 2 different classes and try to determine whether they can distinguish
Between cats and yes.
So for example, here you see that USV is equal to the SVD of the dog 0, cat 0
Yes.
merged matrix.
Yes.
So it's
Exactly.
trying to determine, okay, it's trying to determine. And that matrix dog 0, cat 0, this is DC trainer.
I think I have the process. I haven't taken the entire code. My bad. The process is.
So how many features are included here, Arjen?
Actually, I'm not sure when I checked it. I am not exactly certain.
In the last graph,
The data sets were a bit difficult to pry open, as to say, so I couldn't really.
actually here it's 20.
Yes.
In this slide,
There,
right here.
yeah, there it is. 20, sure.
Okay, so here we have 20. And if we see the last, so let's see, here the features are 20. We are trying to obtain DC trainer, okay. And the final graph that and actually so you have these codes and you get the final, so which numbers do you compare? Or how do you make sure?
I think it's in the Word document. Let me just
It's
check.
in the Word. Okay, okay. Oh, we can have a look there. But you know what, Ari? I was wondering the following. What if you change the wavelet that you are using?
These are the POD modes, specifically relating to the V component of the SVD decomposition.
Okay, okay. But in the codes, I also noticed that you are using HAR wavelet.
Yes, the wavelet was actually the code already used cat and dog classification for, and you did it with wavelets before. So this is just a carryover in a way.
Okay, but I was thinking of the following. I mean, can you check whether HAR wavelet gives a better result or a worse one with some other wavelet, such as the Bechius wavelet?
I could try setting it up. Yes, I'm not sure I can manage it right now, but yeah, sure.
No, not right now. No, don't do it right now. But think about this one.
It shouldn't be a problem. Yes, perhaps it does better.
Okay, okay then. Okay, Ari, thank you for. Anyone else? If anyone has any question to Ari, you can ask him now. Ari, thanks again.
Thank you.
Now, okay. Now I just want all of you to say in 2-3 sentences your topic for the midterm. So we can start alphabetically from Baftiar. You just say in 2 or 3 sentences what your project will be about. Baftiar, can you start first? If not, Bruno. After Bruno, we have Ergen. So I just want to ask about the project of the midterm. Bruno, Ergen, Erida. Bruno, you can write it here. Yes. You just explained to the rest of the class, Erilda or Erinda, since you are in the same group, tell us what your project is about.
Good evening, Professor.
No, say it verbally.
Okay, good evening, Professor. I'm Erinda.
Yes,
Our midterm project consists of digital inline holography. Should I say it in Albanian or English? How do you prefer it?
Whichever way you want. So,
Okay. So
can you
we
add
will...
a couple of more words?
Yes, of course. Holography is a technique that is used. I'm sorry. Do you hear me?
I can. Yes, I can hear very well.
Yeah. Holography is a technique that is used to record a waveform diffracted from an object. And what digital holography is an interferometric imaging tool that does not involve an imaging lens and can be used to perform multidimensional information and simultaneous imaging. We were not ready for today because we talked with you. I think Erilda did to present next week. For today, we have ready. If you want to see the Word document, but it's only the theoretical part.
We understand. Now, regarding your project, what the major expectation is that you understand what the project is about. That's for sure,
yes.
And also the implementation of the computational algorithm.
Yes.
So when you take the digital inline holography, the principles that is used is a Fourier transform of a two-dimensional array. Okay.
Yes.
So we are expecting so that you have the code, you understand every line of the code, you implement it, and the definition of implementation would be the following. You can get an image which is digital inline holography obtained, acquired type of image, and apply this image reconstruction algorithms for us to see what is the improvement, okay?
Okay.
So it should not be only something explaining the theory of what you are doing, but it's good to implement it. Okay, Arinda, this is all I wanted from you, but I just wanted to also specify that what would be my expectation.
Yeah, okay, thank you, Professor, because up till now we have worked only with how to transform on hologram, how to make it digital. So now we will work with what you said. Thank you.
Okay, thanks. Then we can pick some other answers alphabetically. So Baftiar is not Bruno. Let me see if we have Ledio. Ledio is not here. Okay. Ledio is Bruno. You said that you are going to work on but this topic, Bruno, I think it's not for the. It is not for the midterm. It's for the individual presentation. The individual presentation is different, and I believe, Bruno, that's okay. Ergeni, okay. Arinda, Ergeni, Franco. Franco, ç'a teme ke të midtermi? Franco, sheu. Johani, Johanote çfarë?
Fourier picography, Professor.
Okay, so can you explain it in 2 or 3 sentences? What can you say about?
Fourier picography is a computational image technique based on optical microscopy. it constructs the complex image of object, but contrary to holography, it is not it is a non-interferometric imaging technique, and thus often is easier to implement.
Okay. Yeah. Thanks, Johnny. So actually, in your case, again, we would like to see, because you are in a group with another friend, to see the implementation of the code and also presenting it of what it is in principle. And to everyone, what is important is that whenever you are presenting these projects, you should prepare in the Word document also a very relevant list of references, or the bibliographic section, where you provide also the major references when if someone wants to learn something more, they can go over those. And predominantly, you should look for good papers from good journals, okay? If they are in the last 5 to 10 years, that would be the best. If there is the explanation of some approach which was discussed 60 years ago, it's fine. You may include that. So, for example, if you have some algorithm which was mentioned decades ago, you mentioned a couple of publications that talk about it, but also don't forget to include recent ones. Okay, thanks, Johanne. Igli, can you say what is your topic of the midterm? Igli, grazie.
Mua profesor.
Po Igli, më fjalë, në 2-3 fjali, nëse mund ta tregosh, unë e di në fakt, po nëse mund të tregosh tjerëve në klasë, what is your midterm project about in 2 to 3 sentences?
Ok, mund ta shpjegoj me fjalë, por kompjuterin nuk e kam, jo me telefon.
Jo me fjalë, jo, vetëm verbalisht, me fjalë. What I'm asking now is just to talk about the topic of the midterm verbally. That's it.
Një sekondë, lutem.
No, don't worry. We can pick someone else. Nicolini Maimari, can you or we go ahead with Igli. Nicolini, vazhdo ti?
Oh, yeah, yes, professor.
Yes, so 2-3 sentences. What is your topic that you're going to that you are working on your midterm project?
Okay, so my topic is about construction of holographic images using Mie scattering theory. Basically, it uses Mie scattering theory to generate holograms using computational operations. So basically, we are not acquiring holograms, but we are generating them.
Okay, that's good. Okay, Nicolin, now what is essential also in your project, it's a good one, is you have to be able to teach us, to tell us how these holograms are generated. And this one, you can extract this from the code. You have the code, and you have to tell us the mathematical tool or the essence that is doing the trick, okay?
Yes.
So whenever you make the presentation, we will go over the code and we'll ask specifically, what does this line do, etc. Okay. Thanks, Nicolini. Igli, can you go ahead?
Vetëm nuk kam bateri dhe u mundova që ta karikoj.
Don't worry.
Kam projekt SVD, Singular Value Decomposition, që ta përdor SVD në imazhe dhe të llogaris SVD në imazheve dhe të mundohem të bëj detection.
Okay.
Kisha disa cells images, edhe po mundohem të bëj edge detection të këto imazhe.
Okay. Mirë, një gjë që mund të kesh parasysh është që you might have to check carefully how you can enhance the edges of these images by modifying, let's say, I can say roughly, the first 10% of the sigma values in the image, okay? Or, I don't know, the first 3, maybe the first 3 is very little, okay?
Drejt, po e kam bërë, kam shunzuar me një koeficient. Do të thënë kam marrë një range me koeficiente të ndryshëm.
Shumë mirë. You can zero out completely some, how can I say, you can zero out some values, probably the lower ones, you can zero them out immediately. And
Unë e kam bërë në këtë mënyrë që 100 të parat të shumët i kam shumëzuar me një koeficient, apo 10 të parat i shumëzuar me një koeficient, të tjerat i lë 0.
Po.
Edhe jam munduar të bëj reconstruct imazhin. Duhen minimumi 100 të parat që të bëhet reconstruct.
Them diçka tjetër Igli. Ajo që është interesante, ti mund të bësh dhe këtë. Ti shumëzo me 0 ato të mëdhajat, ato të parat, dhe shumëzoj me 4-5, me 4 ose 5, ato të voglat. Sepse duke hequr edhe të features që janë dominante, ajo që për shembull ti ke marrë digital image processing class këtu.
Po.
Dhe është një procedurë ose një algoritëm e cila përforcon edge information in images, e cila është si ndjek këtë hap. Në fillim aplikon një low pass filter, që është i keq që e fshin edge detection, dhe pastaj pasi aplikon low pass filter like a Gaussian filter, you add the filtered image to the original image. Kur i mbledh të dyja bashk, ai që përforcohet ty është edge. So you might enhance the edge by, so let's do this one. So you have an image, you apply a high pass filter, and this is, you enhance the edge, okay? Then what you can do, you can apply, this is high pass filter, and this is also a non-linear filter. So you have also, let me see, you have a non-linear filter, but you can apply also a Gaussian filter, which is a linear one, and this one diminishes the edges, okay? So this is good to preserve the edge, so this is like edge and enhancement. This is like edge enhancement, but now you apply a linear filter, and then this diminishes the edges, but what you can do then is that this is equal to IG, image with a Gaussian filter. And then to make it stronger, we simply say I plus IG, and this results in a very strong edge information. So the edges are enhanced. If we get this image that is filtered, you add it with this initial image. Now, what we are discussing here is that you have the image, you calculate SVDs, and you find some sigmas which go like this, sigma 1, sigma 2, etc. So in principle, you can multiply by 0 from here and the bottom. So you can multiply by 0. So this will be gone. And then see how the image is reconstructed. So you find that this is your S. Then you multiply by 0. This becomes S star, the modified one. And then having U. So the image itself, this is USV, right? You modify it, you use USV, and you find a modified image here, right? So image is USV, you modify them, S becomes S star, you reconstruct the image, you get I star, that's good. But now, most probably, this will enhance the image. But you can also try something which is almost equivalent to this. You can multiply this with 0, so these values are already 0, okay? This is full of zeros. This is how S looks like. But what you can do is that you can multiply these with zeros and multiply this with a factor of 3 to 4 and reconstruct it again and see what you observe. This is USV. Let's call this one S double star because now you have multiplied with 0 this region. And then you can get I double star. And look at the image, how it looks like. Maybe it looks to some degree, maybe it looks, maybe it looks somewhat better. And then you can still do the following. You can add this image I, you can mathematically simply just add them together, and you can have a look if you get something better, or whether you get some enhanced edges. Okay, so this is something that you can think about, Igli.
Okay.
Okay. Then we have here Ina following the alphabet. Ina is going to, I think is working on TSP, but I can give a couple of directions immediately to Ina, which would be that try to see whether the relationship with the area show it to us, and also try to run try to search, whenever you run the TSP, try to reduce the complexity or to reduce the number of paths that you can select. Ina, do you have any question or you want to add anything?
No, Professor. This was our discussion,
Okay,
our previous discussion, but are we supposed to submit those requirements for midterms or?
No, this is
For
for the
the final.
midterm, whatever you have done, the deadline is,
Today.
whenever the deadline is put, that will be the grade of the midterm. Then improvements further on will go for the final grade, okay?
Okay, Professor. Thank you.
Okay, then we have here, so we discussed Ina, Johanni, Nicolini did it. Orisoni, can you go over?
Yes, Professor, my topic was generating matrices to generate Pythagorean triplets.
Okay.
So I found those, I found 3 research papers, one from Bergens, which is from year 1934, and he explains how he found by mathematically found those matrices that when they are applied to the root Pythagorean triplets 3, 4, 5, we can find other Pythagorean triplets, primitive Pythagorean triplets.
So, Orisoni, you, in the literature, you have some matrices that are 3 by 3 that do this, okay? And you can also find other matrices, okay? And once you find other ones, try to find what are the SVDs of these matrices, okay? Or even the ones that are already found in the literature. So we have matrices which are 3 by 3. So let's say you have matrix A, you should find the USV, and please compare. So if you have B, which is equal to U sigma V also, compare these sigmas, okay? Corresponding? And yeah. So please don't miss this part. It is important. Okay.
Okay.
Okay. That's okay. We can stop here now. We can. I want to tell to you the assignment. When I say the assignment, you have to work on it and try to do as much as you can. So the first question, it will be, you are given the runtime for 3 different algorithms that conduct certain measurements. And the first question is, which method is faster? Okay, that's the first question. The second question, which is less important, is the following. So the second question is generate 5 by 5 matrix, and for these 5, but they should be random. Random integer 5 by 5 matrices, and then do this for 5 values. Do this 5 times, okay? And then so maximum value can be 15 of the numbers here. Then do this 5 times, and then calculate sigma 1, sigma 2, sigma 3, sigma 4, and sigma 5, and here you put an end. But you do this one 5 times. And then you have to compare to us report after this is done. Sigma 3 minus sigma 4, okay? And also sigma 4 minus sigma 5. So tell us, what is the difference between sigma 1s? Okay? But
Professor,
by the way, yes.
When you say calculate the sigmas, each sigma for each random matrix.
Yes.
And right, for that we use the.
So then you are going to have sigma 1, it will not have a single value, okay?
Of course.
Sigma 1 is going to have 5 values. So sigma 1, it will have a certain distribution, right? Sigma 2 has also a distribution, but you have to tell the difference between these two. So you calculate sigma 1 minus sigma 2, okay? Is it clear, Ari?
Basically, we're finding the sigma for each vector that's in the matrix.
Say it again.
Basically, we're finding the sigma for each vector that is part of the matrix.
No. So you are going to generate a matrix which is 5 by 5, okay, randomly. Maximum value is going to be 15, and then you calculate the sigmas. So this is sigma 1. You can consider this one sigma 1, 1, Ari, okay? Then you have sigma 2, 1, sigma 3, 1, and sigma 4, 1, and sigma 5, 1. Why are we saying sigma 1, 1? Because this is the first random generated, right? Then you're going to select to generate another random generated matrix. Then you're going to calculate sigma 1, 2, sigma 2, 2, right? Because,
yes.
Okay. So you're going to have a vector which is composed of 5 entries for each of those 5 segments. Good. So you find this, no more explanation regarding this. The final answer, the final question is the following. These are little small exercises, which is the following. Given a matrix A, which is equal to 1, 1 minus 0, 1, 1, 1 minus, what is this? Minus 1, 0, minus 1, 0. And given x0, which is minus 1, 0, find what is a to the power 29 times x0. Okay? Okay, so these are the questions. You can start working on these. But the first, okay.
This is about the homework that the project that we have on class today.
Yeah, this is like something that you are going to write to answer in the class.
We'll do this on MATLAB, Professor?
Whichever language you would prefer.
Okay. Until the end of the class, or?
No, this will be, I'll tell you about the time. You can start working. I might give you like at least, let's assume initially like 15 minutes. And let me say, if you want to use MATLAB, another tool that you can work with is the Octave Online. Can you hear me?
Yes, Professor.
Okay. I thought my internet was down, so Octave Online can be used. So, which is online commands of MATLAB, you can easily run them.
Professor, is there an available command for Sigma, or? That's the question.
For Sigma, I can write this one in the chat section. So you can say the following. You can say USV, this is equal to SVD of the matrix A, okay?
All right, and we just extract the...
Exactly, so, yeah. So, and you have to search for, you have to search, the sigmas are stored in S.
Yes, we extract that one. One question,
Yes.
What is the last one? I cannot read it very well.
Oh, you are given a matrix.
Right, A11 minus 10, X0, okay. I read the two matrices, but then what is the number below, the one?
This is saying A to the power 29 times X0 is equal to what?
e to the power of 29. Okay, got it. Thank you.
You're welcome. All right, thanks so much.
Professor,